In this video, we're going to be learning about oxidation and reduction of aldehydes and ketones so that we can learn to predict the products of these reactions. So all of our reactions for aldehydes and ketones are summarized on this slide. We have oxidation reactions, which can turn our aldehydes into carboxylic acids. Oxidation does not work on ketones. Reduction is the opposite process, and we slightly referred to it during our alcohols chapter, but a ketone can be reduced into a secondary alcohol, and an aldehyde can be reduced into a primary alcohol. We can also have additional reactions across our double bond, and we'll get to that in another video. Our oxidation reactions are very important because once we start our sugars chapter, which is going to be our first biochemistry chapter, all of our sugar molecules have either aldehyde or ketone functional groups. The blood glucose test involves the oxidation of this aldehyde group on glucose. So it is a very important reaction. We can selectively oxidize just our aldehyde functional groups. An example of that is by using what's called Tollen's reagent. Tollen's reagent has silver ions in solution, and so you'll either see it represented as Ag plus or Ag2O or just simply called Tollen's reagent. And it's in a basic solution, so this is a base. This is a base. So in a basic solution with silver ions, and that will turn our aldehydes into carboxylic acids. So this is oxidation. And so this, you might see an O over the arrow to indicate oxidation. Now, an interesting part of this is that since our aldehyde is being oxidized, that means that in other words, since our organic molecule is undergoing oxidation, the silver ion gets reduced. It goes from being a +1 oxidation state to being a 0 oxidation state. Oxidation and reduction technically always happen in pairs. So if our organic molecule is getting oxidized, something else is getting reduced. The silver getting reduced means it goes from an aqueous ion to a neutral metal. Since it's a 0 charge, it can't stay in solution, so it gets precipitated out as a mirror-like finish on the outside of the glass. It's really pretty to look at. So that's how they used to make like those Christmas bulbs, those glass bulbs that are silver. It's kind of expensive now, so they have alternatives, but that is one way to get the inside of the glass completely coated to make a mirror-like finish. We also have this molecule here. You'll notice that this is an alcohol, and this is an aldehyde. The aldehyde is the only one susceptible to this oxidation. The alcohol is unchanged. This has to do with how easily oxidized the different functional groups are, and the aldehyde is easier to oxidize than the alcohol, and so the aldehyde gets oxidized before the alcohol does. Another type of oxidizing agent for selectively oxidizing aldehyde functional groups is Benedict's reagent. Benedict's reagent involves copper ions. Copper ions here are blue, so that's our copper 2+ ions. And then once our organic molecule oxidizes, that means that our copper is undergoing a reduction. So if our organic molecule is being oxidized, our other substance is being reduced. Since oxygen is a 2- ion, that means each plus copper ion here is a 1+ ion, and so our copper ion is being reduced. Its charge is going lower. This forms a precipitate with the oxygen and forms a solid, and so this is kind of cloudy and you can't see through it, indicating the presence of a solid there. Over time, the solid will fall out of solution and be a pile down at the bottom. One thing that's interesting about Benedict's reagent is that in a basic solution, you can oxidize a ketone. You can oxidize a ketone if you have an alpha hydroxy group. So that means that this carbon is carbon number 1. This carbon that's one away at carbon number 2 is also known as the alpha carbon. And so this type of alpha designation means one away from the carbonyl. And this will come into play again once we have our amino acids, because amino acids are called alpha amino acids. Everything's attached to this alpha carbon here. But you can see this alcohol group, which is known as hydroxy, on the alpha carbon. And so this is known as an alpha hydroxy group. And so this will come into play when we do our carboxylic acid, our carbohydrates chapter, because we will have alpha hydroxy ketones in this. And that's because the ketones can do a rearrangement to become an aldehyde in a basic solution. But for now, you just need to focus on aldehydes get oxidized to carboxylic acids. That's what you really need to know right now. And then we'll build upon this once we get into our carbohydrates chapter. So for now, aldehydes oxidize, ketones don't. Don't worry about the ketone oxidation for now. All right, so let's see. Let's mix each of these structures with Tollen's reagent in order to find out what the product is. Go ahead and pause the video and try to draw the condensed structural formula for each of these substances after the oxidation with Tollen's reagent. Unpause the video when you're ready to check your work. Okay, so for our first one, we have butanal, and so that's an aldehyde. And so that is 1, 2, 3, 4 carbons. Aldehydes are always terminal, and so that is an H. After it's mixed with Tollen's reagent, this aldehyde needs to form more bonds to oxygen, and so that's going to form a carboxylic acid. Then we have our carboxylic acid that has 4 bonds. This one's going to need 2 bonds, this carbon's going to need 2 bonds, and this carbon's going to need 3 bonds. For ethanal, that's going to be 2 carbons. One at the end starts off life as I'm just going to draw ethanal. That's ethanal. 2 carbons, terminal hydrogen. After oxidation, this turns into a carboxylic acid. For this last one, we have 2-butanone, so that's 4 carbons long, and a ketone off of the second carbon. So this is the structure of 2-butanone. And after mixing it with Tollen's reagent, we will still have 2-butanone left because this one doesn't oxidize. So we cannot oxidize our ketones because there's no hydrogen bonded to that carbon that we can remove. So reduction is the opposite process. So if we go if we kind of draw it out, if we start off with a primary, that's not a 1, that's an I. So if we start off with a primary alcohol, we can oxidize into an aldehyde, and then we can oxidize that into a carboxylic acid. Carboxylic acid can be reduced into an aldehyde. Aldehydes can be reduced into primary alcohols. Secondary alcohols can be oxidized into ketones. Ketones cannot be, no, can't be oxidized. Yeah. That's not an arrow anymore. Okay. So our ketones cannot be oxidized. And then our tertiary alcohols can't be oxidized. So ketones can't be oxidized. And neither can tertiary alcohols because there's no H that can be removed. So as we reduce, we're adding hydrogens across the double bond. So oxidation, you'll see an O. With reduction, you'll see an H in square brackets, or you might see things like, not Pb, that's lead. With platinum or palladium, you might see H2 with palladium. That's a metal catalyst for hydrogen gas. Or you might see like sodium borohydride, which has a lot of H's. Remember, oxidizing agents had a lot of O's, and reducing agents have a lot of hydrogens. But these are patterns to help you remember things. When we oxidize, we're always taking off one H and making another bond to an O. When we reduce, we're removing bonds from oxygen, carbon-oxygen bonds, and adding back bonds to hydrogens. So chemistry likes to save lives in ways that you might not realize. But muscone, which is commonly, this is muscone, this is muscone, sorry. We can synthesize muscone, which is the odor of musk for perfume industry. That can be synthesized synthetically in a lab now, so that we don't have to kill things like the musk deer or a muskrat in order to secrete this molecule from its anal glands. So whenever you hear like naturally sourced, you have to remember that natural sources include animals and plant products. And sometimes it is better to just synthesize it in a lab so that you don't have to kill animals in order to obtain it.